And this is where we'll start your orbital mechanics is starting. So pay attention here. So you have an inertial frame, okay? And then you have this is your X. Y and Z. And what you have is you have two masses. This is M1 and this is M2. Okay? This is consistent with the textbook 1. This is R1. This is R2. And this is R, small r. And let's say this is RG. So here, you know what this means, right? Inertial frame. It's a fixed frame. Okay. Right. What do you know about R? R is. Can I say R is R2 minus R1?
What's R again?
This is R. This vector.
Going from M1.
Going from M1 to M2.
Yes, that's the thing.
Okay, so you have, if you look at how it is, always remember the vector addition. R1 plus small r is R2. Okay, the tail of the first vector and the head of the second vector. That's the resultant. You understand? So if you see, this is the first vector R1 and this is the second vector R. So if you have R1 plus R as R2, or you can write R2 R as R2 minus R1.
So why wouldn't it be R1 minus R2?
Huh?
Why wouldn't it be R1 minus R2?
That's what I just told you. If you have vector A vector B, okay? This is vector C. C is A plus B. The tail of first vector and the head of second vector makes the third vector C. You see that?
Yeah.
That's exactly what is happening. This is the tail of first vector R1.
Yeah.
This is the head of second vector R. So this can be written as R1 plus R is R2. Exactly the same relation. Okay? So you see this is R2. So you can write R as R2 minus R1. Okay? All these. What is R1? It is absolute position of mass 1. Got it? Because it is
R1 is absolute position.
right, because this is inertial frame. It is expressed in its absolute position. Got it? Again, R2 is absolute position of M2. In reality, what we don't know is, we don't know if there is this inertial frame anywhere in the universe.
Right.
Okay? But we know these two bodies. We know this R. Does that make sense? R is relative position of one body with respect to another body. We always know that. Does that make sense?
Yes.
this could be moon, earth, satellite, moon, earth, sun. You understand? But we don't know this absolute position of sun in the universe. Absolute. Where is that absolute? Where is this point O? We don't know. You understand?
Mm-hmm.
So that is the reason we introduced this. You got it? And this is the, if you take these two bodies, this would be the center of gravity, center of mass of these two bodies. Okay, and this is the absolute position of that center of mass of this two system of mass. Does that make sense?
In the dark circle is the center of mass between the two bodies. The dark circle.
Yes, this is the center of mass.
When you had to label it as RG.
RG, center of gravity. Okay. And what you're also going to see is if these are the two masses, let's say this is M1 and M2, this is F12 and this is F21. Okay? What is this? What could this be?
Force of M1 going towards M2.
This is the gravitational force.
Right.
This body attracts this body attracts this. And F12 is equal to F21. Right? So now you can, what do you know from basics of how do you express RG?
Express what?
RG. RG is M1 R1 plus M2 R2 divided by
2 divided by 2.
divided by
Is it the R? Or the Y?
center of gravity. Essentially, if you look at how you calculate center of gravity, this is how you calculate center of gravity.
Isn't it similar to, I think G1, V1 plus G2, V2.
Something of those ones. Center of this when you are doing this moment of inertia calculation, this is how you try to do it. Okay.
You did M1 and M2 as a mass.
Okay, and this is mass. Okay. Essentially, what you are doing is this into this is equal to this. Okay, you just reverse that. Now, Vg is what? R G dot, correct? This is M1 R1 dot plus M2 R2 dot divided by, what do you know about M1 and M2?
Those are the masses.
Yeah, but
They're opposite directions.
they are constants.
Oh, okay.
Otherwise, this is not the complete derivative, right? I have to take M1 dot as well. You understand? I would have done a product rule. Here we don't do the product rule or the quotient rule. Here we don't do that because masses are constant. But if you cannot do this with a rocket, with launch vehicle or rocket, okay? Mass changes here. So I have Ag is equal to Rg double dot is equal to M1 R1 double dot plus M2 This is essentially the position, velocity, and acceleration of the center of mass.
What does 2 that
Hmm?
mean? Yeah, what does 2 that mean?
Acceleration,
It's like the second derivative.
second derivative. Okay.
Oh, okay.
These dots.
Now, we'll define this UR, okay, and you should be familiar with this by now. R divided by R. Is this clear? UR is essentially the unit vector from M1 to M2. It essentially shows you the direction of M2 with respect to M1. Got it? This would be this would be UR. Okay? The unit vector which shows you the direction of M2 with respect to M1. Got it? It's a direction vector. And it is essentially R, this vector divided by its magnitude. Alright? Now,
Would that be UR1 or would that just be U? Or is it, okay, so if you wanted to do UR.
it's this UR cap. All unit vectors are cap.
Alright, so if you wanted to find some unit vector R1, it would be UR1, you would, or is that unit vector for all three?
So yeah, if you define UR1, this would be that direction. If you wanted to write the direction vector of M1 in an absolute frame, you would say R1 divided by the magnitude of R1. Okay? So that would be the unit vector. Unit vector are essentially direction vector. You got it?
So could there be a UR2 or M2?
Right.
Okay.
There could be, but we don't, it's not relevant here. We don't need that. But we need that. I'll show you why. Okay? You have to understand F12 is the force exerted on M1 by M2, and F21 is the force exerted on M2 by M1. So this M1, look at this, okay, F12. M2 is exerting a force on M1, right? In this direction. Does that make sense?
Mm-hmm.
So it is on M1 by M2. Got it? Similarly, this is exerting a force on this. That is F21. This is on M2 by M1. Alright? What force is this called? What is this force?
Gravitation.
Yeah, it's the gravitational force. So if you write this, now you can see how to write this. F12 is equal to, what do you know about this? It is G M1 M2 divided by R square, right? Keep in mind, recall the universal law of gravitation. Universal law of gravitation states that the force is proportional to the product of the masses and inversely proportional to the square of the distance, okay, between them. And this is UR.
Equals you?
Hmm?
You're saying it's equal to you?
It's in the direction, the force F12 is in the direction of UR.
So you multiply it by U.
This, you see, this is a vector, right?
Right.
This component
Like,
is simply scalar. You have to make it a vector. The force is on that direction. It's in the same direction. F12 is in the same direction as UR. Okay? And then you have F21 is equal to G M1 M2 R square. This is minus. It's essentially UR minus. Okay? So F21 is in the opposite direction as UR. Got it?
or you can write the other way too, right?
Hmm?
Or you can write the other way too, right? Like the first one would be negative, and the second one not.
It depends on how you define this UR. If you define UR the other way, you could have written like that. Okay?
But because we defined it from the M1.
Hmm?
But because we defined it from the M1.
Right. This is how we define. We define U1 as this is very, very critical. How you define this. So what we are trying to do here is, it has a significance in that M2 is so here R1 or small r, pay attention here guys. You can take notes later. R is essentially the relative position of 2 with respect to 1.
Right.
Is that what you are interested in? R is the relative position of 2 with respect to 1. Relative position of this with respect to this. If this is your Earth, Sun, Moon, this would be the orbiting body. Once you know the position, okay, you know the velocity, acceleration, if you just take it away. Does that make sense?
Okay.
So that is, once we define this, the relative position of, we don't know what I told you was, we don't know what this is. But we know these two, and we define this small r as the relative position of 2 with respect to 1. It is relative, if it's like this. You say Akhil, if we don't know where Akhil's absolute position is, but we know the relative position of all of us with respect to Akhil.
Okay.
This is that. So we are only interested in that. As long as we know the relative position of all of us with respect to Akhil, we are fine. You understand? We in the bigger universal context, we don't know where Akhil is, we don't know where each of us is. We don't know this. Even if we knew somewhere with respect to a really, really far off this thing, it wouldn't make sense. You understand?
Mm-hmm.
We want to make sense, make context in terms of something we know, something we are familiar with. You understand? That's the reason we introduced this. And this, when we introduce this, all this is in terms of this. So we define this in terms of this. We define the force on M1 by M2, on M2 by M1. Okay? Which one would we be interested in, this or this? In the practical sense.
Probably the first one.
No, I mean, the second one is right here is R2, R1, so the second one is M2.
Why the second one? Understand the significance of the second one in the context of space mechanics. What is this?
Sorry. Sorry.
This is
Could
the,
be any object.
so we are always interested in
The object that was studied.
Yeah, this is the orbiting body essentially. You understand? M2 is the orbiting body. And we are interested to know what is the force exerted on the orbiting body by the central body.
Okay.
You understand? So that what force is this?
That's the gravitational.
That's the gravitational force.
That's the what for?
Gravitational force. Right? This is the law of gravitation. You understand?
So,
This is the universal law of gravitation.
so the first one isn't gravitational force, or is it gravitational force too? The first one.
If see, you have to understand there are two bodies. This is also exerting gravitational force, this is also exerting gravitational force.
Yeah.
We are all exerting gravitational force. It's not just planets and heavenly bodies. Every particle is exhibiting a gravitational force. You understand? If you take two bodies, the gravitational force is the same. You understand? So here we have just applied the gravitational force. Now what do we know this to be?
Sorry, can you say that again?
Huh?
Which one were you pointing at?
Now see if this makes sense, okay?
Because of that.
This and this. I've replaced this with this.
You replace it with what?
This is the Newton's second law.
Mass.
National accelerator. Okay? And you can write similarly M1 R2 double dot is equal to minus
Dr. Sunday, so why on the second one? So you wouldn't use, so for the mass, you would only use the body that we are located on. You're only using the mass of the body that we're located on?
Yes.
No. This is
I'm
force.
talking
I'm talking about
M1
M1.
R2.
Thank you.
Oh, sorry.
Yes. Thank you, Dr.
This is
It's supposed to be M2, R2?
right.
Okay.
Okay, but this negative is important. Okay? Keep that in mind.
Yes.
Okay. So you see, I've just applied. I showed you how to get the universal law of gravitation. How does it make sense in this whole context? Right? So if you look at what is determining the motion of the orbiting body, what force is it? Gravitation. That's all is there. Okay. Although in reality that is not the only thing.
Right.
But when you're talking about orbiting objects in space, or at least for the scope of this course, we're only considering gravitation force. Okay. Now what happens when this M1 is really big compared to this?
And M2 would get closer to, are you talking about like as in like distance? Okay, so then M2 would get closer to M1.
This actually becomes here.
Okay.
Oh, okay.
So RGB.
RG will be essentially R1. Does that make sense?
Yeah.
Because this is so huge.
It's pulling them too.
Yeah, the center of gravity is essentially the center of gravity of the big body. Make sense?
Can you re-explain this?
For two bodies, okay, this is relative motion, right? If this body, M2, is really small compared to M1, or M1 is really big compared to M2, which is often the case, right? If you launch a satellite, how heavy is that satellite compared to the mass of Earth? Negligibly small. So the center of gravity of a satellite and Earth would be essentially the center of gravity of Earth itself. It would slightly shift, but not a whole lot. You understand?
So like,
It's on the dark
This G, yeah,
will
barely move.
where it's at
If
now.
this becomes really, really small compared to this one, that is often the case. Okay.
so there'd be like a case like
Hmm?
with the center universe, black hole in the center universe.
No, we don't talk about black holes. We don't understand black holes in the Newtonian context.
Stardust.
Okay, so what about our sun?
Yeah, we only limit the discussion to our solar system.
Okay, alright.
Okay, so we don't have a black hole in our solar system. Right? So sun is the center. This is the sun. Even with respect to planets, what we assume is, if you look at, this is an important point of discussion. You look at sun and Earth, right? You are always told that Earth is rotating around the sun, right? Which is the biggest planet?
Which is Jupiter.
Jupiter, right? In reality, Sun and Earth are rotating actually around this center of gravity. Okay? But this is only visible or felt for Jupiter. The Jupiter and Sun, they are doing this. They are not the center of, because Jupiter is so big, even in comparison to Sun, the center of gravity shifts a little bit, or considerably,
Okay.
and they seem to rotate like this around a center of gravity.
So you said it's on Jupiter's still that gravitational.
No, you can actually feel it. You can actually measure it. The measurable difference. Practically speaking, all of them are doing that. Okay?
Does the sun feel it too?
Every object will feel it, but which one can you measure? Which one do you know, or which one can you see, sense?
Jupiter and the sun.
Jupiter and Sun you can really sense. If you have some sensing equipment on ground, you would be able to measure that they are doing this.
Because it's the size of Jupiter.
Size of Jupiter is so huge. All of them are doing it. Okay, all of them are doing it, but we don't have very high precision instruments to measure it or sense it. You understand?
Yeah, how do you know that's not from all other planets combined instead of just Jupiter?
So what we do is we limit our study at 2 bodies at a time. It's a very complex problem to study. There is actually 3-body problem, n-body problem. We break it down into 2 bodies at a time. And it so happens that when we study 2-body problem, the mathematics we are able to use for that are good enough to predict the motion for several hundred years, which is good enough for us, right? We can redo the mathematics. We can redo the mathematics even every 5-10 years and figure out, okay, if it is actually there is nothing called leap year, right? You understand that there's nothing called leap year.
Right.
In reality, you only account for the 0.2526 day of every year, and then account for it in the 4th year, which we assume is a leap year. You understand? So every 4 years we are able to account for that, and then we are able to move on. Okay?
Are you saying the leap year has something to do with your father or?
No, it means that we are able to move on in the sense the mathematics, as you said, in reality it's an n-body problem. You understand? But all of us will have to have a PhD to even study an n-body problem. So what do? We don't study this problem. We cannot do that. We study 2-body problem at a time, and understand? Does the sun rise in the east and set in the west?
On Earth.
Well,
Yeah.
it depends on the
It
perspective.
doesn't. Is your point that it doesn't rise?
I mean, you know what I'm talking about when you learn this, okay? In school.
No.
I mean, go ahead. I mean,
That's what you've been told, right?
Yeah.
Is that true?
if you're on Earth, or is talking about
Not necessarily.
Does the sun rise really? Or Earth is setting?
No, that's right. But
Earth is moving, right? Earth is rotating. And that's what causes the. You're not going to say, go to NASA or Air Force and say the sun rises in the east.
you know, but like if the sun was, if we can see the sun in the same light, and we point towards the sun, it would be in the easterly direction.
The Earth rotates into a position in which we can see the
You
sun.
don't want to say, if you have kids, you still want to tell them, yes, sun rises in the east and sets in the west. At a NASA discussion, you don't want to say, oh, the sun rises in the east. They'll send you back to.
Send you back to Tuskegee.
You have to come here and relearn the whole thing, okay?
First, you can't tell your kids that the sun rises. You gotta tell them exactly how it is. Don't sugarcoat it. Show them the map.
That's what happens.
Make them understand.
Because what's this?
So what we'll end up today is, we'll finish here. So you have, so this is all, see what have you learned here? Think about what have you learned here.
How you can use the
This is all absolute, okay? We have not used this term, you see? This is a relative term, right? But we have not used it. This is, again, absolute, right? This is also absolute. R1, R2 are absolute, right?
Yeah.
But we are not really interested in that. You understand? What we are really interested in is, or what we can really understand is, R double dot is equal to R2 double dot minus. Correct? You with me? From this. Okay? I'm just going to what is this?
This, that's the acceleration of.
Well, minus G M1 over R squared minus G M2 over R squared. And this whole thing is got it? So this can be written as minus G R square, right? And you can write this as M1 plus M2. Got it? You with me?
Yes.
Yes. What did we say? If I'm going to erase this part, okay? Just going to write here R is equal to R2 minus R1. If M1 is much greater than M2, then M1 plus M2 is equal to with me? Okay, so you can write R double dot is equal to minus GM R divided by confusing GM 1 over r square r divided by r. This m is essentially the mass of the central body. I replace this m1, m2 by, let's say m1, but for completeness I'm just going to say it's the mass of the central body.
Of the what?
Central body.
Central body.
So you have the central body and the orbiting body. You got it? Make sense? Here, this is what? Gm is what? We represent that by mu. Okay? And this would be r divided by r cube. Okay, and if you combine this is r double dot plus mu over r cube. R is equal to 0. This is the two-body problem. So see what I did here. Guys, pay attention here. You're with me on this one? I substituted for R2 from here. I substituted for R1 from here. Okay? This, you see, M2 M2 cancels, M1 remains over R square. M1 M1 cancels, only M2 remains. Okay? And UR is common. So this R is equal to minus G over R square, M1 plus M2 UR. If M1 is really big, which is the case, right? In what we are studying, then we can simply write M1 plus M2 as M or M1, let's say. Okay? I'm just going to write this as M. The mass of the bigger body, the central body. Got it? So I have replaced this by R double dot is equal to minus Gm. This M1 plus M2 is M divided by, multiplied by 1 over R square. UR was simply R over R. You see that? If I multiply this will come Gm. Gm is what? G is what?
GM.
G.
Oh, G is gravity.
It's the gravitational force, right? Of the gravitational constant. This m is also a constant, right? So Gm is just a constant. We'll replace that constant by mu. This is called the gravitational parameter. It's again a constant, right? And this is R, vector R divided by R cube, scalar R cube. R square into R is R cube. Okay? And if you move this on the left hand side, you're going to get this, which is this is the two-body problem statement. You got it? Any questions?
You're not going to ask us to divide this, are you?
I'm not going to ask you to do that.
The test next week will cover just chapter 1.
Chapter 1. You still can't.
Hang on guys, let me take your attendance. Okay?
Right.
Marcus, just a minute.